Critical Transitions in Complex Systems seminar series is being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, popularly known as PIC in Germany, Potsdam. This seminar series brings together experts from a very diverse set of fields such as climate science, ecology, combustion, fluid mechanics, neuroscience, etc., and aims to disseminate the state of the art and the prediction of critical transitions in these diverse fields of study. The seminar series usually takes place every month on the last Monday of the month. There are some exceptions, but usually we try to keep it that way. Before I introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones and please use the Q&A box in Zoom to ask the speaker your questions. We have kept ample time at the end to discuss your questions. And today we have a distinguished speaker, Professor K.R. Srinivasan. Before I let Jürgen introduce him formally, I'm happy to say that he is now the occupant of Professor Rodam Narasimha Chair at IIT Madras. Rodam Narasimha is Professor Srinivasan's PhD supervisor. So over to Jürgen for introducing the speaker.
Yeah, thank you very much, Sujit. I'm really very, very happy to shortly introduce our today's speaker, Professor Kattepalli Srinivasan. I'm sure you all know him. He is one of the leading, maybe the leading scientist in fluid dynamics and made a lot of basic contributions on especially turbulence, but also on applications in engineering, climate, and other fields. And very successful, and he got a lot of honors. But let me only shortly mention that he started his career to get his master and PhD in the Indian Institute of Science in Bangalore, then made a short journey via Australia, UK to US, became as a very young scientist already professor at Yale University, then went up to higher and higher positions, then went also to Maryland University, one of the main hubs in complex system science. But at that time, in the beginning, he has become director of the International Center for Theoretical Physics in Trieste, where he worked several years. And this was very important for the ICTP, but also for us in complex system science, because he helped us a lot to organize meetings, conferences, schools, etc. And this was really great. But then he went back after US to New York University, got there also high positions as vice provost, but is still professor at the Courant Institute of Mathematics, and got, as I mentioned, a lot of prizes, awards, member of several academies in US, in India. I'm very happy that he is also a fellow of the Academia Europe, which is very important for us to have such famous and world-known scientists. But I will stop now, otherwise I would steal you all the time for your talk, Srini. I will not. Please, you have the floor, and we are all very interested in getting your recent research. Please.
Okay. Thank you, Jürgen, and thank you, Sujit, for inviting me to give this talk. I was a bit apprehensive that it may not fit into the big scheme of things you have in your seminar series, but Sujit assured me, and Jürgen assured me as well, that it does fit in, and so I am very pleased to be giving this talk to this group of audience. So I will speak about decaying turbulence, and the substance of this is contained in these two papers, especially the second one, which will appear sometime soon. So let me state what the problem is. It's very easy to state. So you take a volume of fluid and you stir it well and then stop stirring. And because of viscous action, the turbulence that you have generated will decay. The question is, what statistical laws does the decay of energy follow? This is the most fundamental problem of turbulence. because many other things that you normally encounter in turbulent flows do not exist here. It's a homogeneous flow. It can also be made isotropic, and so many of the processes that occur in normal turbulent flows don't occur. And the main thing that remains, or perhaps the only thing that remains, is nonlinearity. That is energy transfer from one scale to another. So it's very difficult in the sense that what remains is nonlinear, completely nonlinear. And as I said, things like coherent structures and so on, some of which is linear process, do not exist here. Okay, the problem has been around for a long time, since 1940s, and it's fair to ask, have we solved it yet? And it is in this spirit that I will want to tell you a little bit about what's been happening lately. So the equation for this decay of energy is really written down very simply from the Navier-Stokes equations as d by dt of the kinetic energy, which I represent by k, is equal to the energy dissipation rate. So the energy that is there in the turbulence gets dissipated in some fashion, and that's all there is. And the most important dynamics then is where the energy is and how it goes from where it is to where it gets dissipated through the transfer across scales. And this simple looking equation has enticed many studies, theoretical, experimental, and lately numerical, with varying degrees of sophistication. But I regret to say there is no solution for this problem, and we will discuss that towards the end, whether that statement is still true or not. And the most basic expectation is that for some significant range of time, the power loss of this sort exists. That is, the energy decays like a power law in time, t to the power minus n, and the length scale of turbulence grows as t to the power m, where m is a positive number. The length scale grows because as small scales, as the decay proceeds, first small scales decay, then the next set of scales, and so on. And whenever the small scales decay but the big scales remain, effectively the length scale increases. So the question is, what are these indices n and m? This, as I said, necessarily involves nonlinear spectral transfer of energy and so on. There is one simple case for which there is a solution, and that is L does not vary, for instance. That is, it has grown to such an extent that it has filled the entire space that is available for the turbulence to expand. And so L is constant, so M is 0. And then the so-called dissipative anomaly holds. That is, there is a relation between energy dissipation and the energy itself. And then you can see that it goes like t to the power minus 2, and experiments confirm this, as we have shown before. But let's leave that aside for now. Now, how does one realize this experimentally or in practice? We are interested not just in theory, but also in making comparisons with experimental realizations. The simplest one is the periodic box in a simulation. For example, you can have a big box which has a fluid in it, let us say, and it's periodic. That is to say, what goes in one wall goes out through the other opposite wall, etc. There are no solid walls. And you stir the box a little bit and leave it there and see what happens to the energy. Or experimentally, you take a water tank and you take a grid like this and you pull the grid through. It creates turbulence, and you want to ask yourself what happens to it as a function of time. Alternatively, you can take the same grid and put it in a wind tunnel and let the flow go past it. And then, as you can see, near the grid, somewhere here, you can see all these wakes distinctly, but they all mix together to give you a homogeneous looking turbulence, which of course changes as you go downstream, but this change is sufficiently small in comparison with the decay itself that you might regard time and space as interchangeable in this fashion, and you can study what happens to this turbulence. It's called grid turbulence. So these are the ways in which you can realize the flow. So what are the classical theories? Since it's been around for a long time, obviously there are theories. And I want to call attention to one set, which is the theory is based on the existence of invariants. So first one is due to Kolmogorov, 1941. He assumed the so-called Lorentziansky's integral to be invariant. The integral is shown here, which is r to the power 4 times RLL, which is just the correlation between u and u in the same direction L. So if this correlation decays fast enough, then the integral r to the power 4 times that exists. And this thing could be invariant, as Lorentziansky thought. If, let's say, the correlation does not decay fast enough, then you can see that this integral need not converge, and you have problems as you go to larger distances. And in fact, Batchelor and Proudman showed that the integral exists, but it is not invariant. Suppose it is invariant, Kolmogorov showed that the exponent n is 10^7 and m is 2/7. And this existence of an invariant in this form also means that the energy spectrum E of kappa, where kappa is the wave number, it goes like k to the power 4 for small k. I will not show this, but it is very easy to see that. So near the origin, it's going like k to the power 4, and it is non-singular. And I call this LKB after Lorentziansky, Kolmogorov, Batchelor. And there is a second one, which was begun by Birkhoff, and it was worked out much more completely by Safman in 1968, who demonstrated, I put in demonstrated in quotation marks because there are some technical details. He showed, instead of the Lorentziansky integral, whose existence he doubted, actually has this integral r squared RLL of r dr to be invariant. That is, now there are less stringent conditions on how fast this RLL decays. This is equivalent to saying that the spectral density near the origin has the form ck squared for small k, and that yields n equals 6/5 and m equals 2/5. I call that BS after Birkhoff and Safman. Please do not refrain from thinking of what BS brings to your mind all the time. Now, each of them is related to a particular type of behavior of large scales, that is k near 0, that is the wave number is small, that is the length scales in physical space are large. So each of them relates to the particular behavior of large scales, and their invariance, if it exists at all, is described as the permanence of large eddies. What does this mean? I can explain this to you very simply. On the horizontal axis is the wave number, and on the vertical axis, the wave number divided by energy per wave number. And the spectrum, the one at the very top, let us say, is what you sort of put in. So this is some power law here near the origin, and then like minus 5/3 or some such power for larger wave numbers. And as time proceeds, what happens is that this part of the spectrum actually does decay like this, but this part near the origin stays unchanged at all. This is the whatever you put in initially will remain k squared or k to the power 4, whichever is right, and or whichever you create. And this is the so-called permanence of large eddies. So the large eddies sort of remain the same. The small ones are the ones that decay, and larger and larger ones begin to be affected, but the largest ones still remain invariant. That's the theory that existed. And what about the experiments? There have been many experiments, but the most convincing ones were made in 1966. And what is plotted here is 1 over the energy as a function of time. And you can see that there is on a log-log plot here, a straight line showing you have a power law. And the authors fitted a power law for that with a slope of 1.28. I want to call attention to a few things. The extent is about a decade or so, not much larger. And in fact, two components are slightly different, as you can see from the two different symbols. And what they had to do in order to get the best power law was to imagine there was a virtual origin which they subtracted from the actual time they measured, which means that there is some kind of fitting that is going on. Nevertheless, these were the most convincing experiments that were made in the late 1960s and or mid 60s, and people were very convinced that there is in fact a power law. And years later, I made the same measurements again in the same wind tunnel when I went to Johns Hopkins, and I found a slightly different power law, which was 1.2, and also found that the length scale varies as a function of time in this fashion. And this is what I call L over M, that is the length scale divided by the mesh size, goes like x to the power 0.4. X is to be treated as time in this case. This was in 1980 or so. And so the general thought has been, you remember what Safman showed, n equals 6/5 and m equals 2/5. And you can see that the length scale goes like 2/5 here, and the measurements that I just alluded to actually go like 1.2, which is not that different from 1.28. And the problem seemed to have been understood at least at some level, and it stopped being of primary interest maybe from 1970s itself. However, I was giving a talk in the summer school, and I thought, well, let me revisit this problem, and started collecting all the exponents that people had measured. And here is a histogram of the exponents. Surprisingly, if you look at the histogram in the experiment on the left and simulations which had come into being in the meantime on the right, you can see the exponent varies from 1 to 1.5 or so in experiments, and from 1 point something to almost 2 in simulations. This clearly is not acceptable, and there is no unique exponent at all. I was quite surprised to find that out, and which we would like to understand. And both experiment simulations, extraction of n is problematic, however. And it's problematic because of the main reason that in experiments, measurements were not carried out for long enough. That is to say, you have sometimes less than a decade, like a half a decade or so. It's always dubious what kind of power law you can fit. And there's a pragmatic idea of adjusting for virtual origin, and there were some anisotropies that were present, which means that the grids were not carefully constructed. And some authors fitted power laws from very close to the grid. For example, what does that mean? If you have a flow like this, you're fitting it very close, like the vertical line shows, and that is not even fully developed turbulence, so you never know what it means. And I have to say that I had pointed out in 1984 already that there is a non-uniqueness in this depending on what type of grid you use. So the physical, so if you want to really understand this well, you have to vary the conditions on the grid and initial conditions, or the origin, and doing it physically, experimentally seemed very difficult. Diverse and controlled conditions are hard to get, and so we thought we would do the simulations. And we did the simulations. In particular, I want to point out that in experiments, you cannot go for very long in time, and therefore you're always limited in the extent of the power law that you can fit. In the simulations, however, you can go for a lot longer, and here is one simulation which John did in 2022. This is time going from 1 integral scale to 1,000 integral scales. You remember that experiments were of the order of a decade or less. And what you find is that the energy normalized by the initial energy actually, after a small adjustment period, follows a very nice power law. And to see that it is indeed a power law, you take the slope of this line, you plot it here as a function of time, you can see that it is nearly flat, approximately 1.25 or so in this case. However, John also did a number of other experiments, a number of other simulations, and here is a list of them which you don't have to worry about. Shockingly, the local slopes, instead of being flat, as you would expect for a power law, and in fact you saw in one case, and if you had stopped there, we would have thought it's all fine, shows all over, results all over the place. So the status report is power laws are not always found, even though you can sort of fit if you wanted by looking at the data for a very short distance. Where power laws are present, as in some cases they are, the exponent is not always the same. It differs from one case to another, and this variation seems to result from different choices of initial conditions. So here was where I had stopped about 4 years ago, let's say. And then I gave a talk, and Migdal was present, and he said, "Oh, I have a theory for this." And so Migdal nudged me with his new theory, and then my student Akash Rodhiya, he gave substance to the work by doing the simulations. And I must say that the initial theory of Migdal was all over the place. And in fact, it was anchored by the simulations that Akash did over time. So this is what I will now describe to you. What is Migdal's theory? Let's talk about it first. I will only speak about it in very rough terms. And then we can discuss more if you want. The theory has the so-called loop equation, which I will describe, and then some magic that is put in, and you get some very important results. So what is the loop equation? You have Navier-Stokes equations, and Eberhard Happ, many years ago, 1950, actually cast it in functional form, which is actually linear, but it is infinite dimensional, and nobody knows how to solve that functional equation. Now, what Migdal did was to cast it not for velocity, but for circulation around loops. Now, circulation around loops is something he had been thinking about in QCD. And of course, it has some very nice properties, as we showed some years ago, and which got him excited. So anyhow, he formulated the equation in terms of the circulation for the loop. Now, that equation is also in functional space and it is linear, and it's actually looking like a linear diffusion equation. So if it is looking like a linear equation, you can Fourier transform it. But if you Fourier transform it, because it is infinite dimensional equation, it's still very difficult to manage. And he used the WKB approximation, that is limit of small viscosity. Now you have a much simpler looking equation which he can actually solve through what I call his magic. And what he found was the solution for the equation that results here is one that randomly traverses the vertices of a polygon of many sides, actually infinite number of sides if viscosity goes to 0, itself randomly oriented in a sphere, and this is in some fancy space that is neither physical nor wave number or anything like that. And he calls that universal Euler ensemble. This is the attractor for the decay problem, and its invariant measure is computed, lo and behold, from number theory. So this is the magic that I talked about. And what he found is that the energy decays like the minus 5/4 of the time. And where does this 5/4 come from? It doesn't come from Navier-Stokes equations, but it comes from number theory, which is what he used. And this zeta 0 is the Riemann's zero of Riemann's zeta function. And that's what you have. Why it should be Riemann's zeta function, why number theory must have anything to do with Navier-Stokes turbulence, etc., is something we can discuss. And the other result is he defined a length scale in this fashion, which is the first moment of the spectrum, energy spectrum. And that grows like half power the time. And then he also had an expression for the slope of the second order structure function, which in the force case at very high Reynolds numbers must have a slope something like 2/3 if Kolmogorov is right, or some small deviations from it. And then he also showed that large wave number spectrum should go like a to the power minus 7 halves. So these are the results, and we want to see whether there is any evidence for this at all, especially because of the route which this solution took in order to get these results. So we did these simulations, very large simulations in a very large box, periodic box, pseudospectral solvers which everybody in the business knows about and work very well, time marching schemes, and the boundary conditions are periodic, as I said, on this box. And we can do a very long-term evolution by varying tricks that we used. So initially, the spectrum is prescribed as shown in the bottom left. The low end of the wave number is some power of the wave number itself, 2 or 4 or whatever, and then you have a 5/3 spectrum followed by an exponential decay in the viscous region. Now we put this in and let it go and see what happens. And I just want to call attention in this table that simulation time goes to something like 20,000 or so, 280 in this case, the time scales. So you can actually see the evolution very, very clearly and convincingly. We don't go always that far, but you will see the results here. So now, for the BS conditions, which is that I prescribe initially the spectrum to have going like k to the power 2 for very small k. And you can see the energy here, I call this En instead of k in this case, as a function of time, normalized by the initial turnover time. And different Reynolds numbers here, different Reynolds numbers have different power laws, but as the Reynolds number increases, you get to 5/4 very closely over an extended period, extended time scale. And in fact, if you want to be a little bit more picky, you can take the local slope of that and plot it here. And you can see that for very low Reynolds number, it sort of dips to something like a 1.25, but not exactly. It is higher than that, as you can see here. And then it takes off. But as the Reynolds number goes up, you can see that it approaches 1.25 and stays flat on this line, at least up to a few thousand of the integral scales. So that seems good. About the length scale after some initial adjustment period here of a few scales, a couple of scales, it seems to have a slope of slope of 0.53 instead of 0.5. Actually, if you adjust for this somehow, you can plot the time here and length here. You will see a very nice parabola with a small adjustment here accounting for this kind of thing. And the two lines here, one of which is a simulation and the other is this formula, and they agree perfectly. And for the slope of the second order structure function, for which I have given the expression, you can see that if you plot this f of x, which is the slope effectively, versus logarithm of r, in this case the separation distance, and the theory is this orange line, and the simulations are this blue line with the shaded area, which is the one standard deviation. In fact, except for maybe very large distances, the agreement is really excellent, and maybe here it is certainly within a couple of standard deviations. And for the LKB conditions, that is Lobachevsky-Kolmogorov-Bachelor conditions, again, the slope of the structure function is shown here in good agreement, you might say, and here is the length scale, and I have again given you this parabola, which fits extremely well. So should we declare this as a victory for the theory and then move on or not? Unfortunately, there are some complications still. So for the LKB conditions, for which I already showed you some results and they work very well with the theory, the energy decay, however, follows minus 10�7th power, not minus 5/4 power as the theory predicts. And in fact, it stays like that for a few thousand scales, as you can see from this decay exponent plot. Now, what is the matter with this? You might say. Somehow, I thought perhaps it could be minus 5/4 plus some correction of some sorts. And if you are used to, say, what people do in condensed matter in general and so on, you can put as I've shown here, minus 5/2 plus some other power here, minus 11/2 comes from another time included. But Migdal's theory says, well, that's not how you should do the correction, but actually the correction occurs at the index itself, and that's minus 5/2 plus something that goes like the minus third power of the length scale. And if you do that, what this curve where the theory and simulations do not agree actually tend to agree after a first few time scales in the problem. So might be, perhaps you can say, maybe this is right, maybe this is how we should fix it. But it is still not quite exactly as you might have thought immediately. Another thing is, let's say the energy decay is not unique because the energy is a large scale quantity, and the large scale quantity is affected by very large scales in the flow, and these large scales are affected by the boundary, and the periodic boundary conditions probably have an effect on that. And so instead, you look, let us say, at a quantity like enstrophy, which is the vorticity, and you can, which is not influenced so much by the large scales, and you can measure it as a function of time. And what you find is that there are, this is um, these two lines or the simulations which go for long times, and one slope is 2.25 and the other is 2.42. I don't think there is any ambiguity that in fact the two slopes are different. Again, you can uh, do the correction as Migdal suggested, and here are four cases that I have shown here, and these are the data uncorrected, so to if you want to call it like that, and the red lines have always been the theory, which do not agree, as you can see. But if you make the correction the way Migdal suggested, you bring these data points, so to speak, onto this line, the red line, and that happens to be true in all the cases that have been examined. So I almost come to the end of my talk. There is one aspect that remains still unclear, and that is the energy spectrum itself. You remember that Migdal's theory says that for large wave numbers it goes like minus uh, 7/2. Of course, it doesn't consider actually the dissipative scales. It's only in the scales that are not influenced by viscosity. And here is the actual energy spectrum that is measured at different for different times, from 70 to about 1,000, and they all collapse on each other more or less when you plot against the Kolmogorov normalization, although they differ here because of the so-called intermittency. Nevertheless, that's the shape of the spectrum. And if you insist on putting a minus 7/2 power, it'll be something like a tangent somewhere, and that's probably where it happens. So this obviously is not true, at least for these conditions. And if anything, this spectrum can be fitted by something like this, which is a kind of theory that we made up. And this, if you plot the logarithm of E of k here, derivative of that with respect to log k, which is this quantity, it has this form, which is shown by these graphs, and this table here gives you all the parameters you find empirically. So this new work has been exciting. You have all these things like field theory and number theory and hydrodynamics and turbulence, all of this sort of stuff coming together in some fashion. So it's been exciting in some ways, and if it is true, then there is something very deep and fundamental that we still have to pay attention to. But has it been solved yet? This is the question that I asked at the beginning. And so I have to give you a very cautious response to that. Meticulously performed DNS results show that low wave number behavior dictates the decay rate in periodic boxes. And of course, the periodic boxes have a problem um, in some sense, although they approximate the homogeneity um, as best as possible. And at least for these cases, there is no unique decay law for the energy. And this is not very surprising to me that the energy, which is a large scale quantity, can be affected by many things, is not the case. But in fact, Migdal's theory is this impressive theory, let us say, comes up with a unique attractor for the decay problem, and it has a unique decay exponent and things like that. And this theory, as I said already, combines hydrodynamics, field theory, number theory, etc., etc. Now, simulation theory are in perfect agreement for one case, which is the BS case, and can be made to agree well after a bit of plausible nudging for LKB, which we can discuss. That is to say, uh, add another term to it, which is the next order. Um, Although the theory for that next order has not been worked out as well as the theory for the first order. And that's the reason we should discuss that. And certainly there is still one aspect needing further explanation, the spectral behavior at high wave numbers. Now, one might say that, well, because the Reynolds numbers are not high enough, the the decay part of the spectrum encroaches upon what this -7 horsepower should be, and endows it with another more complicated behavior. You might say that this is a standard answer that one might give in turbulence, always saying that the Reynolds number is not high enough. It may be true or may not be true. But if this is not true, that is to say, high Reynolds number is not the impediment, then you have the issue of how to explain this, how to incorporate this observation into the theory, or vice versa, remains an issue. So that's the status of the decay problem. That is to say, there are some very exciting developments in the last few years. And the conclusion is optimistic enough for us to persist with it for a little bit longer in this direction, but it is still leaving a little unanswered questions. So thank you for your attention. We have a reasonable amount of time for discussing the results.
Yeah, thank you very much for this great talk, Srini. Very impressive. But maybe who will take over the
I am
discussion?
doing okay now. So
Okay.
since there's a Q&A box. I don't know if you can see it.
I can see the box.
Yeah. So in that already there are 4 questions here.
4 questions.
One starting
Yes,
Rajara. Would you want to read out or
show,
you?
no, let's see. Now I have to be able to see it.
Yeah. Okay.
It is there, but
You click on that, and there'll be more boxes.
no. I click on it and nothing happens.
Oh, okay.
That's what is happening. So it says, okay, let me see. All right, I found that. And Rajaram Lakraju says, why the curves always so deep and they grow near small time. So these things are that initially you have a spectrum that you put in, which is sort of arbitrary, in the sense that it comes from random initial conditions, and it takes a little bit of churning through the Navier-Stokes equations before it assumes the properties of turbulence characteristics of Navier-Stokes. So that's the reason you have these changes. Exactly what that shape is, nobody knows, but the fact that it should be different from the asymptotic law seems to be very reasonable. So can we define a zeta function that maps a fluid flow? Well, this I don't know. I don't know the answer. And somehow at the end, the solution to this problem that Sasha casts in terms of the loop functional equation for the loop somehow has this property. If you solve it, it has to have a property which is discrete. That is to say, it has to jump from, let's say, if you have you may not see my fingers, but if you have a polygon of some sort, and then the solution randomly goes from one vertex to another vertex in some random fashion, and um, this plane of this polygon also changes randomly with time within a sphere, in some infinite dimensional sphere. So there's some mathematical issue there as to whether what the limiting conditions are, whether this all is valid as the number of vertices in the polygon goes to infinity and all that. Leave them all aside, which of course other mathematicians have looked at now very carefully. But now that's the solution, and the solution uh, uh, is just coming from the Riemann zeta function, and I don't have any idea why it should be like that, and I don't know if anybody has the idea. So if it were traditional Navier-Stokes, you write it down and you sort of follow through, which is what people tried to do in the past. It hasn't been very successful, but here is another approach which is coming from some other left field, so to speak. And then you have a theory based on very profound mathematics theory, and it seems to have results that are in agreement, at least up to the point that I discussed. And why it should be and why it is so is totally amazing to anybody. It may be, let's say, a coincidence, in which case it's too much of a coincidence. And if it doesn't work, I don't know, do we have a right to say that it should agree in every respect? I don't know. If it doesn't, of course, it is not a theory at all. Now, then there is another one by Lacrage which says how to understand Migdal length. Now, the thing is that there are length scales in the problem which have been defined in the past. For example, the integral length scale. Integral length scale comes from taking a UU correlation, or what I call LL in the talk, and then the correlation is unity for for a unit for zero time, and then it diminishes for larger and larger time. It should be zero for very large time. Anyhow, we know that. But you have a boundary, a finite boundary, whether it is periodic or whether it is a internal or whatever, for large times, there is influence of the boundary, and you cannot depend on what you measure for the actual behavior in the theoretical sense. So now this length scale that Migdal defines is the first moment of this thing. So it is sort of not the length scale; it's the correlation itself that whose decay you want to observe, but it is multiplied by 1/r kind of thing. So it decays definitely faster, and therefore it converges, and that is the main advantage of this length scale. It is still belonging to the large scale, and physically it has the advantage of convergence. So that is the reason for it. And the follow-up question is, Riemann zeta function involved means is there summation or variety of energy scales involved, any fractal-like structure? There is a fractal-like structure, in fact, and no, you didn't misunderstand that part. I think that seems certainly the fractal structure comes from this random jump from one vertex to another vertex in some random fashion, and the randomness comes because of the initial conditions which are random in this functional equation. And then Anirudh Shivakumar asks, how do these scaling behavior work in the context of quantum turbulence? In quantum turbulence, all the measurements have not actually been made in as much detail, but the one problem to which I drew attention very schematically in the very beginning was when turbulence expands in such a way that it fills the entire domain, um, that is available for the turbulence, the length scale stops growing, and then you can actually find the solution to be uniquely t to the power minus 2. And these are the experiments that are actually made in quantum turbulence. And because the apparatus are usually very small, we could wait long enough for turbulence to expand and fill the entire thing. And we found minus 2 just as expected from the theory. And in fact, this came from quantum turbulence, and in fact, it has been verified since for the classical one. So that is Anirudh's question, and I think I have answered all the ones that are on
Yeah.
the yeah.
Yeah, so this almost looks like magic to me, all the things that you showed in
Yes,
connection with.
it is, yes. This is why I called it magic, yeah. Yes.
Yeah.
But there are certain things like that in nonlinear dynamics. It's always full of magic, it seems to me. Period doubling, why should it work? For instance, in cases where it has no business.
Yeah.
So now, what has the logistic map got to do with, let us say, Rayleigh-Bénard convection at very low Rayleigh numbers? Now, what do we include from it? There is some universality to it, and the universality you can work out by looking at some particular aspect of the problem, a particular aspect, and if it works, you are lucky, and if it doesn't work, I don't know what to say.
Okay. Thank you.
So I have another question, which is sort of longish, anonymous attendee. In electrodynamics, the Aharonov-Bohm effect shows that a particle can be influenced by a potential even when the local field is zero, yes? In fluid mechanics, we have situations where the vorticity is zero locally, but circulation is non-zero, and so the flow remembers a distant vortex. In the context of decaying turbulence, do such non-local topological effects play a role in how energy and structure remaining during decay? Now, circulation is the integral along a contour, as you know very well. But Stokes' theorem, it is also the integral of the vorticity that is contained within the loop of the over which you are doing the line integral. So it may be related to vorticity elsewhere, and in fact, it usually is. But as far as your computations go, it is coming from what is inside the loop altogether. And these non-local conditions always play an important role in fluid dynamics, because Biot-Savart law tells you how the vorticity and the velocity are related to each other, and it is always a small power law, and so you have large effects of non-local conditions. I can't comment on the exact relation between Aharonov-Bohm effect and what happens here, but I think a rough answer is what I have already provided.
Jürgen, Ambika, do you have any questions or points?
Yeah, I have no questions, but an interesting talk. I'm happy to meet Professor Srinivasan after such a long time.
Hi,
I heard him
Ambika,
first
how are
in
you?
19 yeah, I heard him first in 1987 in the workshop in IISc Bangalore. So nice to see you again. It's a very interesting talk. Yeah.
Well, thank you. It's been a long time. Yeah.
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 Maybe one point is with perturbations from outside. When you have such levy noising, as some bumps also, as in the atmosphere, when you have volcanic eruption or so, then this is disturbed for some time. Can it go also then to another scaling, sometime, some transient time?
This case is you initially set up the energy in some fashion, and you allow the turbulence to uh, proceed on its own through the decay of energy. And as long as that condition holds, it should apply anywhere. It's slightly different for the case of, let's say, volcanoes or things like that, because unlike the case that I have just explained to you today, in volcanoes, not only is the energy produced at the origin of the volcano, but even as it proceeds, it continues to produce a little bit of energy. And therefore, this whole thing has to be modified, but it is not very hard to modify using some simple arguments. But theoretically, that is coming formally in some rigorous way, it's not clear at all. So the exponents do exist for that, and they'll be different from what the exponents are in this case. But the analysis can be very similar.
But what I had in mind is what we call multi-stable states, and that there are several coexisting states. And you think it's not so easy to bring a turbulent system due to some push into another turbulent regime.
If you have a fully turbulent state with a very large number of degrees of freedom, it is not very easy to do that. But if you are still at a lower Reynolds number, so where you have unstable states, you can in fact make it go that way, just as you say.
Okay. Yeah. Thank you.
Okay, I think we had a good talk and lots of questions. I want to thank the speaker for this wonderful talk. And before I close, I want to say that talk about next talk. We are delighted to announce that our webinar will feature Professor Jeff Mollis from the University of California, Santa Barbara, USA. The talk is on 20th April, which is at the same time as 20th April. So this is not the last Monday, but the on Monday before the last Monday. So look forward to seeing you in April. Thank you, Srini, once again for your wonderful talk.
Yes, Sujit, could you put me on your email list, and then I can get a Zoom link as well, and
Yes.
I might join some of them. Yeah. Thank
You're
you
on.
so much. Thank you, Jürgen. Thank you, Sujit,
Yeah.
Ambika. It's very nice
Bye.
to meet you after
Bye.
all, and thank you all for for attending this. I know there were 67 or so
There
at some
were
point.
85 during the talk.
85. Okay, all right. So I'm happy to know that.